The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
So, thank you, Dave. I'm here to cause a little bit of trouble. Last week, I was reviewing a paper written by one of my students, and the student wrote a very good document. But the only problem is that the general tone of the document was, all you old guys are stupid. So we managed to tone it down a little bit so that those of you who are denying that you are old will not actually reject the paper. But I must acknowledge quite a lot of the stuff that's in this presentation is from Jim Grove from Federal Highways and from Dr. Ezgi Yodekol sitting in the back row trying to hide. I'm going to cause some trouble and ask some snotty questions and challenge you about the way you think about things. And maybe we will say that ACI 211 isn't that the best document and we should think about it slightly differently. So the first thing we want to do when we're looking at the idea of proportioning, Dave's already done a lot of this introduction, is, well, what are we trying to make? We're trying to deliver a mixture that meets some sort of requirements. And the bad news is that most of the requirements that are in current specifications are not useful. Having figured out what we want to deliver then, we start to fool around with the proportioning side of the game, which is looking at, okay, I've got this material and this material, how much of each? And that's going to be the focus of the next 20, 30 minutes or so. So let me ask the question. Typically, your state DOT specification says slump, strength, and air content. Right? Anybody want to challenge? Eric, come on, argue with me.
We don't care about slump.
You don't care about slump. He's been listening. He's heard me rant on this before. In fact, I was at a DOT recently, and the chief engineer was sitting in the front row, and I made that statement that, why bother with slump? And the answer was, because we've done it for the last 40 years. That doesn't answer my question. Why bother with slump? What does it do to predict any of the engineering properties that we're really worried about? Yeah, I had to leave that room from the back door. Okay, the other one I really enjoy about this image is if you have a look, if we talk about quality assurance, at least one of these beams is twisted. So is that going to give us a false low or a false high result? False low. So while the concrete's perfectly good, the data point coming back is going to be low. The contractor's not going to get his bonus on this day. Yippee. Okay, so, and the other question I like to ask crowds, when did you last have a pavement fail because it wasn't strong enough? That's the response I normally get. So why do we spend so much time fussing about strength? Okay, I'll get off my rant. And we should be starting to think a little bit more about, we're dealing with a harsher environment. The new de-icing salts we're putting down. They're fabulous from the point of view of the driver. I nearly spun this morning on the half-inch of ice that was down on our Iowa roads this morning. I was very pleased to get behind a salt truck laying down a lot of material. Meant I made it to the airport. But these salts are actually pretty aggressive. They make the environment a lot harder. So the stuff we've been doing for the last 40 years may not be good enough. We're also dealing with new materials. ACI 211 was last modified in 2001? No, 1991. All right? Fly ash has changed a lot since then. Cement has changed. Admixtures have changed a huge amount since then. Are we following the same old rules of thumb, and are they still appropriate? The way we build things is different. Paving machines are getting bigger and heavier and stronger. We can deal with stiffer mixtures. We're pumping to the top of 100-floor buildings. That's a challenge. So everything is getting a little harder for us. We can't continue to do things the way we always did. All right, the other question I want to put out here, thinking about this on the way in. How many of you actually do the exercise of number crunching a set of mixed proportions? One. So what are the rest of you doing here? All right. There is a perception, the topic is coming up often. I'm getting a lot of requests for it. And I think it's because as we start to talk about durability, sustainability, that there is the hope out there is that we've been over-designing our mixes. There's a silver bullet. If we just figure out a new way to do it, we're going to solve all our problems. Maybe. And that's why I'm quite happy to spend this time. But that's why I'm also laying down a big foundation of what are we really trying to do as we tackle this exercise of number crunching. Okay. So Dave's already alluded to this. What should we be measuring? Yeah, we should be measuring workability. Slumps on, not it. Is there a better test? No. Are we working on it? Yeah, Tyler's got one. I've got one. He and I are arm wrestling. You'll hear about his a little bit later. Measuring permeability. Is there a good test for permeability? No. Those of you who call it the rapid chloride permeability test, go back and read the method. Okay? The Wenner resistivity probe is probably as good as any we've got at the moment. What has it got to do with freeze thaw? Nothing. So it's still an indication. It's not an answer. Okay, strength we do need, because structural design is based around strength. But it's not the end of the game. One day when I'm feeling really brave and the answer to every maiden's prayer, I will go into ACI 201 and cause trouble. I haven't quite got that energy yet. Shrinkage. How do we measure that? Every specification I read has got a slightly different version of it. We should be measuring it. It controls cracking. That's critical for pavements. What about the air void system? How do we measure that? Okay, so there's challenges out there. We can do a whole lot better than we've got right at the moment. All right, here's where I pick on ACI 211. It was developed before water reducers, before supplementary cementing materials, back in 1991. It was designed or set up by structural engineers chasing 4,000 psi in a 4-inch slump. So, how many pavements are built that meet those criteria? Okay, let's keep going. This is a concept I stole from Eric Kohler. I think it was part of his PhD at University of Texas. Although it's not actually original with him. It's not very different from what I was teaching undergrad students 25 years ago. The basic model that he put together is that you figure out your aggregate system, then you figure out the quality of the paste. Let's use the dazzle. There it is. There we go. Figure out the aggregate system. There's a black art in getting that one right. Then figure out the quality of the paste. That one's actually pretty easy. That's what's in the spec, or in a good spec, anyway. Then we put the two together and figure out how much paste do we need to put into the aggregate system to get the mixture that we want. And this was the basis of Esgy's PhD. So let's look at the details. This is a chart from data I collected with an undergraduate class in 1980-something. Right? This is not new. The way we used to teach it is that we'd drag the students into the lab, we'd get an air pot, and do consolidated bulk density of the rock. Flip out 20% of the rock with sand, and measure the CBD again, and again, and again, and you get a curve where it starts low, gets to a maximum, and goes down again. So then the obvious question is, where do we want to be for our sand-stone ratio for these two materials? Duh. Somewhere around here. Why? Because rock is cheap, cement is expensive. Cement paste shrinks. All right? So we want a reasonably high amount of aggregate in the system. Do we want it in absolute maximum? Maybe not. And I'll show you why in a couple of slides. But we want it somewhere up here in this sort of region. The other way that we look at the aggregate system is the combined aggregate gradation. And we've all read Jim Shilstone's work. We've all played with his charts, the Power 45 chart, the workability factor chart. And until now, they've been about the best that we've got. Have they been ideal? No. But it's been the best that we had. The next critical part of the process for me, and this may be the innovative part, work out how much space is inside the rock. So you've got the consolidated bulk density of the rock-sand combination. How much air is left in between there? And that's useful to know because we want to fill up all of that space with paste, and we want to add a little bit more to make sure they're glued together. So, void ratio is a term I will come back to. That's what it means. All right, so we're targeting a good combined gradation. We're also targeting aggregates with good quality in terms of potential durability. And Dave has discussed all of that, so I don't have to. All right, one of the tools that we've used, stolen from the asphalt industry, is this idea of the Power 45 curve. You put the horizontal axis to a log 45, and you draw a straight line from the smallest particle to the largest particle, and you try and force your gradation system to sit tight on that line. The theory is that if you're hard on that line, you're going to be pretty close to the absolute maximum amount of aggregate you can get in there. With a couple of caveats. If it is hard on that line, it may not be workable. And the other one is that the Air Force or the airfield guys, there's a consultant out there who says no, he likes it to drop off below the curve, round about the number 16 sieve, because in his observation, and this is purely empirical, is that if you get it to deviate from the Power 45 a little bit, then sliver spalling goes away on airfields. And all the airfield people jump up and down and say, yes, no more FOD, this is a good thing. But he couldn't tell me why, and he couldn't be too explicit about how much. But we want to be off the curve just a bit to provide some space for the paste to get into. So I did the exercise. 2 aggregates from local suppliers. There's a quarry in Ames, produces a really good limestone, and we got a river gravel for the fine aggregate. And the best combination we could get with these 2 materials is this red line. Not very pretty, but it's what everybody builds with in the county I live in. Is it ideal? No. Do we get away with it? Yes, because there's a lot of really good pavement out there built with this aggregate system. All right? So then I did the theory thing. This is hard data. The red is hard data. I then created on the spreadsheet a beautiful aggregate, a 3rd combination that would make it fit tight on the Power 45. So I was going for that maximum density. Okay, so the red is real, the blue is theory. I'm still looking for some more money to make sure that what I'm producing in the blue actually works. If anybody has a check, see me afterwards. You're supposed to laugh. Thank you. Especially the academics, right? All right. Then we got a curved ball. Remember I talked about maximum density is not ideal. How far off do we go? We don't know. Tyler Lay will do a full 30 minutes on this discussion at the end of this session. But he's developed what he's calling the tarantula curve. I think his grad students are a lot cheaper than mine, or they work a lot harder, but they've done many hundreds of combinations of aggregate systems and measured workability using the box test, and Tyler will go into a lot of detail. But the output of that is this envelope. It's not the 818 curve that you may be familiar with. The top end is at 20, not 18. The bottom end is at 4, not 8. And there's this hump in the middle where it goes low. And Tyler's position is that if we get a gradation inside this curve, we're going to be a lot better off in terms of fresh properties, workability of the system. And this is fabulous because so often I've gone to conferences, I've listened to people that do mixed proportioning, that get out in the field and fight with a mixture in front of a paver. And so often they'll say, oh, well, if you take out 200 pounds of the number 8 or the number 16, it all works. And I'm going, why? How much? When? What's a good number? Yeah, well, it worked on this site. Tyler has finally done it where he's got, here's the envelope we want to be inside. This is fabulous. This is new and great stuff. Listen to him when he comes up here in a couple of speakers' time. So then with that same set of data that I've already showed you, the red was the real materials I get in my neighborhood. The blue was with my beautiful conceived artificial combination. And what I also did was put a third combination together, theoretically, that tried to fit a little better inside the tarantula. You can see the red gets outside the top end here. My theoretical got outside in the middle range. And so I've created the little blue dotted line, also theoretical. Now, the critical part of this, the voids inside this aggregate system, of the two aggregate system, was pretty high, 23%. By taking an ideal system, that drops by over 3% to just under 20. If we take a theoretical tarantula curve, it's only just above 20. So we're still reasonably dense, but off the maximum a little bit, but only off it a little bit. So again, absorb those numbers, memorize them. They're part of the quiz at the end of the session. Okay, so we've got our aggregate system. That's the hard part, really, because often we're confined by what do we have available, what's affordable, those sort of problems. When we start talking about the quality of the paste, it's a little easier. We want to think about what supplementaries do we want to put into the system and how much. And it depends, again, what you have available. Slag, fly ash, silica fume, some combination of these materials, even a ternary system to get the best possible material that meets your durability, long-term performance needs. We choose our water-cement ratio. At the moment, based on experience in Minnesota and the fun that we're having with joint deterioration, my recommendation is that for pavements in a cold environment, target a 0.4. If you get 0.42, I'm good. If you specify a 4.5 and get a 4.8, you're looking at joint deterioration. Don't come back to me and complain. Okay. How much air do you need? Again, we've done a little bit of work trying to make sure that the recommendations developed in 1952 by Kliger were great for type 1 cement, no admixtures, no supplementaries. Does that rule still apply? Actually, it does, remarkably. It's still pretty good that we want about 5 to 6% air behind the paver. And there's the rub. Charles Nye is not in here, so I can say admixtures seem to be less stable. And I'm seeing it often. You get 6% in front of the paver and you get 3% behind the paver. Is it going to be durable? No. The other one is we get 6% in front of the paver and 16 behind the paver. And then your strength goes south. So we have to watch out for the stability of our materials and calibrate for them for the equipment that we are using. All right. Then we start looking at, well, how much paste do I really want? So if I want lots of workability, I put in very little aggregate and lots of paste. Is that a good concrete? Okay, there's no coffee in the room, but try a little harder. Thank you. All right, so you tell me that too much paste is a bad thing. I'm an engineer. If you tell me something's a bad thing, I'll take it all out. So here I have very little paste and lots of... That thing's not going to shrink. Is that a good mixture? Why? No workability. And the other issue is there's actually no glue in the aggregate touching points, so your strength's actually going to go south. All right, so this is why engineers make the big money, is that we have to fight with learning the black art of balancing contradictory signals. So that's why we go with a graded aggregate system, and we make sure there's enough paste to keep those aggregate particles separated. 2 reasons. 1, the paste is the lubricant in the fresh concrete, keeps things moving. It separates out those hard, lumpy aggregate particles and makes them flow past each other. The other thing is that the paste is the glue. So at the end of the day, those aggregate particles stay together under whatever abuse and load we put into the system. So the trick question is, and this is what Ezgi answered in her PhD, was how much more? Ezgi? Can you remember? It was a year ago. Oh dear, I've abused her enough. All right, the background to the work that I made her do was that I grew up in an environment where we didn't specify cement content. We specified water-cement ratio, and it was up to the lab to figure out how much paste we needed for the aggregate system that you had. So when I came to this country and I came across specs that said 564 pounds of cement, I was going, I'm going back in time. Ah! But it took a PhD at an American university for me to get any credibility. All right, so if you want to argue with me, that she's sitting in the back row. All right, what we did is that we made mixtures with 400, 500, 600, 700 pounds per cubic yard of binder. We worked at fixed water-cement ratios, and we measured strength, permeability, workability. All right? And what we found, hey presto, if you haven't got enough paste in the system, you've got pervious concrete, and it doesn't hold together. Are we surprised? No. You get around about 500 pounds per cubic yard. For that same ugly red line aggregate system, we got reasonable strength. In this case, the chart is strength. We got up to 600 pounds per cubic yard for a fixed water-cement ratio, and our strength's got a whole lot the same. 700, the same. So the trick question I ask engineers is, adding cement, does it give me any better strength? And everybody goes, yeah, no. There's my data. In fact, I abused Ezgi when she first produced this chart, because it looked exactly like the model that I was saying, this is what it should look like. And so she came back with these numbers, and I said, yeah, all right, those are my numbers, where are yours? Those are her lab data. These are real numbers. Okay? And in fact, strength may actually decrease with increasing paste count. The one that really got my attention was this chart. Here we have got the paste to the voids ratio, the volume of paste divided by the volume of voids in the aggregate. Remember the volume of voids in the aggregate we talked about, and I made you memorize it? All right. The volume of paste is some multiplier of that number. Here we had, at 90%, it's unworkable. At 130%, it's unworkable. At about 140, 150%, we start to get workability, and we've got soup once we get up in the high numbers. The really interesting thing about this was that my instruction to her was, get me 4 inches of slump. Use whatever admixture you have to. I think we were running at 2 or 3 times manufacturer's dose down here, still not getting any slump. There just wasn't enough paste or water in the system to get it out of the ground. Once we do get it out of the ground, it takes off pretty quickly. Up here, there was no admixtures added, and we were well above. So it's not how much admixture we put in, it's how much paste and the workability of that paste that we put in. All right. This is a combination set. 6 different research projects, 3 or 4 different laboratories, many students. And it looks a little crowded, but I managed to draw a curve around it. I learn from my students. But the envelope basically shows us that it goes up, it reaches a peak, and it goes down again. Now this is for zero slump to self-consolidating concrete. It's a whole bucket load. All right, and the peak is around about 175%. So you measure the voids in your aggregate, you multiply it by 1 3/4, and that's how much paste you put into the mixture. Pretty simple, really. And just to back it up, yeah, I know it is noisy, but the orange line is one consistent set of data joining similar mixtures. And in fact, in this case, the strength is decreasing slightly with increasing paste content. What was really interesting is that the permeability data showed significant decrease in performance with increasing paste content. Oh dear. Oh wait. Aggregate is less permeable than paste. More paste, higher permeability. Logical. All right. Dave tells me I've got 2 minutes left. I might make it. Putting it all together, for a typical mix with the red, ugly 2 aggregate system, with that 1.75 multiplier, we need about 520 pounds per cubic yard of paste to make concrete. Yeah, that's about what they're doing in practice in my neighborhood at a 0.45 water cement ratio. If I want a 0.4, I've got to put in a whole bunch more paste because I've got less water in the system. But if I have a well-graded combined system, I can save myself close to a sack of cement and get the same performance. So that means that a 0.4 water cement ratio, I can still be less than 500 pounds per cubic yard with a well-graded aggregate system. The little dot on the top here, that's the tarantula curve. So this is ideal, maximum density. This is tarantula curve. If the tarantula curve gives us durability and workability, and we can get durability at 0.4 water cement ratio, we can do this. We can make hand-placed concrete for pavements that survives at no extra cost. I like that. Dave made the point already, and that's why I can stop here. You have to get into the lab and do trial batches. We're working with a test that measures vibration versus penetration of a fixed shape object. And what it's clearly showing me is that for materials with different mixtures with very similar initial slumps, that I can separate out the effects of fly ash, added water, silica fume, excess aggregate. I think I have something there. I'm not talking about it a whole lot. I need to do some more work. But I believe we have a method that will tell us how does this system perform under vibration without having to pay $30 million for a slip-form paving machine. Any questions? Anybody want to argue?
Okay, time's up.